We want to evaluate the limit as x approaches infinity of 1 over natural log x minus natural log x over x. Now, we can go ahead and use the laws of dominance here. So we can think about this first term, and as x is approaching infinity, I have a constant over this logarithm as a function of x that's getting really big. So a constant over a really big number is 0. So this first term, as x is approaching infinity, is 0. Now, this second term, I have a logarithm on top and x to the first in the denominator. So I have a logarithm and a polynomial on the bottom. And so that polynomial is going to get bigger faster than the logarithm. So it's similar in form to over here where the top is constant and the bottom's getting bigger faster. Well, the logarithm is getting bigger, but the polynomial is getting bigger faster. So if the bottom of the fraction is getting bigger faster, then the whole fraction is going to 0. So we have 0 minus 0, which is not indeterminate. 0 minus 0 is just 0. So we want to be, aware that we can think of each one separately. If we did get an indeterminate form, like infinity minus infinity, then what we'd want to proceed to do is combine these into one quotient so that we could use L'Hopital's rule. But that wasn't necessary here. Now we want to evaluate the limit as x approaches infinity of natural log of the absolute value of x minus 2 minus natural log of the absolute value of x plus 1. Now, if we look at these two terms, if I think about as x approaches infinity, so if I substitute in x into each of these natural log functions, each of these natural log functions is going to infinity. So I have the infinity minus infinity indeterminate case. So I need to try to do some more work here to see how I can rewrite this so that it can be determined. So what I'm going to do here is recognize that I can use a log property. So I want to be thinking now about L'Hopital's rule where I need a quotient. So how do I turn this into a quotient? Well, there is a log property that we're going to use. This is equivalent to the limit as x approaches infinity of the natural log. So when I have subtraction between two logs with the same base, and these are both natural log, it becomes natural log of a quotient. So natural log of the absolute value of x minus 2 over the absolute value of x plus 1. So we can actually rewrite that as the limit as x approaches infinity of the natural log of x minus 2 over x plus 1 in absolute value bars. So now I can see a quotient in there, right? And so I can actually think about what is the limit as x approaches infinity of that quotient x minus 2 over x plus 1. So these are both polynomials, top and bottom. They're the same degree, x to the first, x to the first. So let's remember that as x approaches infinity, if the degrees of the polynomial are the same, then the answer is just the leading coefficients taken over each other. So the leading coefficients are 1 over 1. So the limit as x approaches infinity of the inside of this is that part's just 1. So what I have is natural log of the absolute value of 1. Well, natural log of 1 is just 0. Now let's look at the limit as x approaches infinity of the natural log of the quotient x over the square root of the quantity x squared plus 4. So what we're thinking about is the limit as x approaches infinity of this quotient part on the inside involving x, right? So we're focusing on this part here. Now the top is this polynomial, this line, x to the first. The bottom is interesting. The bottom, the square root of the quantity x squared plus 4. Well, towards infinity, that plus 4 isn't really going to matter. So what we're really focusing on here is the square root of x squared. And the square root of x squared isn't simply x. The square root of x squared is the absolute value of x. Or technically, it's both positive x and negative x. That's what absolute value means, right? So the square root of x squared is the absolute value of x, which is x and negative x. So x when x is greater than or equal to 0, and negative x when x is less than 0. So it is a piecewise function. So which piece do I use, right? Positive x or negative x? Well, since x is approaching infinity, we're going to use x values greater than 0. So the bottom here is essentially just x. Towards infinity, it's behaving like the function x. So we can just focus on the part that's x to the first. And well, the top was x to the first. So once again, the same degree, x to the first, we get to take their coefficients, which is just 1. So the answer to this is natural log of 1 again. And natural log of 1 is 0.